Point 3. Constant acceleration equations. How do we use equations to describe and predict motion? This is going to lead us to make a lot better predictions using these equations. Here are some of our objectives. Be able to identify the meaning of each symbol in a constant acceleration equation. Understand that constant acceleration equations only apply to constant accelerations. If you don't have constant accelerations, you're not going to be able to use these specific equations. Apply a constant acceleration equation to solve a physics problem. There's your pages if you are following along with that book. Table of contents, less important to you. Constant acceleration equations of motion. 4 equations that relate the quantities of motion when an object travels with constant acceleration. Do you remember this? Right. Let's let it play again. Okay. The equations we are about to learn apply to only motions with constant accelerations, only if you have a straight line on a velocity versus time graph. If you have a changing acceleration or a curve on your velocity versus time graph, that means we're going to need to input calculus in here. Okay, so this is going to be your big red flag. Do I need to use calculus or not? If you don't know calculus, then you're probably not going to need to use calculus. Remember that constant acceleration means the velocity changes by the same amount every second. If acceleration is changing, we can't use these equations. We would have to use calculus. I said that. Let's figure out the first equation from a typical velocity versus time graph for constant acceleration. Remember from our linearization, y equals mx plus b, the slope-intercept formula. Well, in this case, the y-axis is v. Our slope, what is the slope of velocity versus time graph? Acceleration. What is the x-axis in this case? Time, plus our y-intercept. That's just our initial velocity. The intercept is the initial velocity. That's what I just said. So we can change the slope-intercept equation for a line, the velocity as a function of time equation. Velocity as a function of time. Remember, that's a different way of saying v versus t for a graph, right? So all we're doing is translating that graph into an equation. There it is in all of its glory with vector symbols. Time, not a vector. Velocity, acceleration during this interval, time spent, accelerating velocity. There we go. If v equals at plus v naught, then we can label v, at, and v naught on the graph. The initial velocity, y-intercept, acceleration times time, the slope for length of time, and finally the total velocity is everything on that graph. Keep the lengths v naught and a times t in your mind for the next slide. We can figure out the second equation by remembering that the area under a velocity versus time graph is change in position. We split the area under the graph into a rectangle and triangle because I know how to get the areas for those shapes. The height of the rectangle is v naught and the width is time. Therefore, this area of the rectangle is v naught times t, right? Length times width. The triangle has a height at and a base t, so the area of the triangle is 1/2 the base times the height, or length times width divided by 2. 1/2 t times at gives us 1/2 at squared. Displacement is a change in position, the final position minus the initial position, and displacement is the area of this graph. So then displacement, the final position minus the initial position, equals 1/2 at squared, this junk right here, plus this junk right here, v naught times t. If we solve for just our final position, we would add the initial position to each side, and we would get the equation that looks like this. x position after this interval of acceleration. A equals acceleration during this interval. T is time for this interval of motion. V naught is velocity at the beginning of this interval, and x naught is position at the beginning of this interval. Remember, this x sub 0 is pronounced x naught, not, but not. Note, each of the terms on the right side represents a distance, as in final position, initial position, distance that the object travels because it has an initial velocity, and distance the object travels because it has an acceleration. Remember the old v equals x over t, and if we solve for x, we would get v times t. Well, that's it right here. And then from the graph, we have this 1/2 at squared. No time. If we're not given time, we have this equation for us. We can take the two equations, v equals at and v naught equals, and x equals 1/2 at squared plus v naught t plus x naught, and combine them together to make a third equation. What we do is we solve for the v versus t equation for time, then plug in the time into the x versus t equation, then simplify the algebra. We're not going to show all the math, but the result needs to be known, and that is this. V, this is our final velocity squared, speed at the end of the interval, acceleration during this interval, displacement during this interval of acceleration, and the initial speed. If we remember the equation, delta x equals v times delta t, displacement equals velocity times time. We can't use that equation if an object is accelerating because v has to be constant. But we can always use the equation delta x equals v average times delta t if we're using the average speed. When an object has a constant acceleration, the average speed is simply the average of its initial and final speeds. So we have this equation. The initial and final speeds divided by 2. So the average of the initial and final speeds times t plus the initial position. Position at the end of the interval, average velocity during this interval of acceleration, displacement during this interval, and the initial position. Now, of these four equations, this is the only equation that is not given to you for your AP exam. I don't really know why. I guess it's pretty easy to figure out. Either way, that's just what we have.